This video is on part 2 of our cryptography material. So the cryptosystems that we've talked about up to this point, that is Caesar's cryptosystem and the permutation cryptosystem, those are both what we call symmetric key cryptosystems. What that means is that if, say, the encryption key is known, then it's easy to determine the decryption key, and vice versa. I mean, another way of putting it is that if you know how to encrypt a message, then you very easily know how to decrypt a message. So, as I said, there are monoalphabetic examples of this, including the Caesar's cryptosystem and the permutation cryptosystem. In this video, we're also going to investigate some what are called polyalphabetic examples of symmetric key cryptosystems. These two examples are going to be the Vigenère system and the Hill cryptosystem. So now polyalphabetic cryptosystems have an added feature where the encryption of each plaintext letter depends not only on the letter, as in the monoalphabetic examples, but also on the position of the letter within the text. So this should make it harder for an attacker like Eve to break the cryptosystem, because the exhaustion method and the method of frequency analysis could both be problematic to employ. First, we describe the Vigenère cryptosystem. So we pick a number m, a positive integer m, and our key, our encryption key, k, instead of being a single number in Z26, is going to be a list of m numbers in Z26. Then, to encode a plaintext sequence, x0, x1, x2, etc., we encrypt each symbol one at a time, where the encryption of x sub j is a shift of x sub j by k sub I, where I is congruent to j mod 26. So as in the Caesar cryptosystem, spaces and other punctuation are ignored. All right, to get a feeling for this, let's use the Vigenère keyword donut to encrypt the message, grade my homework. So first, somewhere on a piece of paper, it's good to have written down a list, our standard list of how numbers are associated with letters. So A is associated with the number 0, 1 is associated with the letter B, 2 is associated with the letter C, and so on and so forth. And then finally, 25 is associated with the letter Z. So it's a good idea to have that written down somewhere. Now, our Vigenère keyword is donut. Well, how does this feed into this scheme? Well, D is the third letter in this scheme. So the D in donut corresponds to 3, so that will be K sub 0. O is the 14th letter. N is the 13th letter. U is the 20th. And T is the 19th. So our K keyword, or donut, gives rise to the key whose components are 3, 14, 13, 20, and 19. So now to use this to encrypt the message, grade my homework, let's first write out the plain text. So we have grade my homework. And now we're going to assign each letter in Grade My Homework its corresponding number from this list, and that becomes 6, 17, 0, 3, and then E is 4, and then 12 and 24 for my, and then homework is 7, 14, 13, 4, 22, 14. And then 17 and 10. So this is sort of the plain text message, P for plain text. That's the plain text message translated to numbers. And now what we're going to do is insert our key. So the point of this key is to cycle through all of these shifts. So our first shift is going to be by 3, our second shift by 14, third by 13, fourth by 20, and fifth by 19, and then we start over again with 3, 14, 13, 20, 19, and then start over again, 3, 14, 13, 20, and then 19. And then to compute the ciphertext numbers, we just simply add the plain text numbers to the shifts in Z26. So 6 plus 3 is 9. 17 plus 14 is 31, but that's equal to 5 mod 26. And then 0 and 13 is just 13. And then we have 23. And 19 and 4 is again 23. 12 and 3 is 15. 24 and 14 is 38, which is 12 mod 26. And we have 20. 14 and 20 is 34, which is 8 mod 26. Then we have 32, which is 6 mod 26. And then 7, 10, 1, 12, and 3. And so the encrypted message, if we now go back up to our list of the way letters correspond to numbers, this becomes JF NXX, and then PM, and then finally UJGH, KBMD. Okay, so this is the ciphertext, the final ciphertext message. Now, one thing I want to point out to you about this, and this is what is going to make this Vigenère system sort of less susceptible to frequency analysis. Notice here we have the letter E appears twice in the plain text message. But in the ciphertext, one of the E's is encoded as an X, and the other one is encoded as an H. So one charming feature of the Vigenère cryptosystem is that it smooths out the frequencies with which letters appear in a piece of ciphertext. So here, we're going to imagine we've got the Vigenère cryptosystem again with the keyword donut once again, as on the previous slide. We're going to compute the expected frequency of the letter A in a piece of ciphertext. And here we mean out of 10,000 symbols. All right, so first of all, how can we achieve the letter A as a piece of ciphertext? Well, A, remember, corresponds to the symbol 0. And how can we get the symbol 0 as ciphertext? Well, we would need to add 3 to something, or we would need to add 14 to something. Remember, our key, if the keyword is donut, then the key itself, the numerical key, is 3, 14, 13, 20, and 19. So again, to achieve the letter A, which corresponds to the number 0, we would have to add either 3 to something, or 14 to something, or 13 to something. Or we would have to add 20 to something, or 19 to something, where all of these equations are occurring within Z26. So this first equation would say that x is 23. The second one would say that x is 12. The third one is x equals 13. Fourth, x equals 6. Right, 20 plus 6 is 26, which is equal to 0 in Z26. And finally, x equals 7. Now, those correspond to plain text letters X, M, N, G, and H. Right, so over here, we've got the ciphertext that we're interested in, which is the letter A, and it is achieved from these plain text letters, X, M, N, G, and H. And now, what are their frequencies out of 10,000 symbols? Well, we can use table 10.1 from our text to see that the frequency of X would be 9. The frequency of M would be 145. N is 554. G is 126. And H is 419. Okay, so this comes from table 10.1. And so then the expected frequency of the ciphertext A is going to be 1/5, right? Which is the probability that A comes from, one of these particular 5 symbols times each of the sum of the frequencies, right? 9 plus 145 plus 554 plus 126 plus 419. And that turns out to be 250.6. Okay, so far we've been doing all of our arithmetic in Z26. However, Z26 isn't an ideal arithmetic because Z26 isn't a field, right? 26 is not prime, so Z26 is not a field. So we can remedy this by augmenting our alphabet with the space character, with a comma, and with a period. So this would bring us up to 29 symbols. which we would number 0 through 28. And that would allow us to identify our new augmented alphabet with the field F29. So the Hill cryptosystem is another one of these polyalphabetic symmetric key cryptosystems. But there are a few differences here. First, the key is, instead of being a number or a list of numbers, is an invertible M by M matrix with entries in F29. And instead of encoding one letter at a time, we're going to encode a block of letters at a time. In fact, this block B here is of size M. And to encrypt this block B, what we do is we just multiply B on the left by our key matrix K, and that should give us another string of length M. Okay, so an example is good here to do. So let's look at what happens when M is equal to 2, in which case the key matrix will be this 2 by 2 matrix with entries 3, 4, 2, and 3. And we're going to encrypt at least part of the message, "I saw Bigfoot." Now remember that we're working with our augmented alphabet now, and so that means that spaces, commas, and periods are part of our alphabet, so we need to make sure we don't forget those things. All right, so the first thing we're going to do is to, let's encrypt the first 2 characters. So the first 2 characters are I, and then the space character. Okay, so the letter I corresponds to the number 9, and the space character is the number 0. And therefore, to encrypt this, what I should do is take my key matrix, which is 3, 4, 2, 3, and multiply it by the string 9, 0. So when I do that, I get 3 times 9, which is 27. That's a legit member of F29. And then when I take 2 times 9, I get 18. So that means that the first 2 characters of our ciphertext are 27 and 18. So 27, you might remember, is the comma, whereas 18 is the letter R. Okay, so that's the first 2 characters. And then we go to the next 2 characters, which would be S and A. So S is character number 19, and A is character number 1. Right, so to encrypt that bit, we take our key matrix, 3, 4, 2, 3, and multiply it by the vector 19, 1. And then we have to see what that gives us. Well, the first component of that product is going to be 3 times 19 plus 4 times 1, which is 61. But remember, we need to reduce mod 29. And so we find that 29 goes into 61 with a remainder of 3. And then in the bottom, we have 2 times 19 plus 3 times 1, which is 41. And mod 29, that is 12. So that means that the next 2 characters of ciphertext would be letters 3 and 12, which would be C and Character 12 would be L. So that means that the first 4 characters of our ciphertext are comma, R, C, and L. Okay, so I will allow you to continue on with the rest of the encrypting to get the ciphertext for this. So just like with the Vigenère cryptosystem, for Hill's system, attacks by exhaustion and frequency analysis are not efficient. So there are a couple of viable attack methods, however. One is what's known as a known plaintext attack. So here, Eve here has obtained some pairs, M sub I, comma, C sub I, where M sub I is plaintext and C sub I is the corresponding ciphertext. So if she can do that, then she can break the Hill's cryptosystem. And even better would be this chosen plaintext attack, where Eve has obtained some ciphertexts, C sub I, corresponding to plaintexts, M sub I, that she has chosen. Here we're going to mimic a known plaintext attack on Hill's cryptosystem with M equaling 2. So Eve knows that every plaintext message begins with good morning. And today's ciphertext begins with the 4 characters AQMA. So the question is, what is the key matrix for that day? So let's take a look at this. So we know that good corresponds to the characters 7, or to the numbers 7, 15, 15, and 4 in our extended alphabet. That includes, remember, the space character, the comma, and the period. On the other hand, we have this ACMA that corresponds to the word good. And those numbers are 1, 17 for the Q, and then the M is 13, and A is 1 again. So let's suppose that our key matrix K has entries A, B, C, D. So our goal is to figure out what A, B, C, and D are, and that will require some work on our part. So what do we know? Well, we should know that if I take my key matrix and multiply it by the first 2 characters of the plaintext, I should get the first 2 characters of the ciphertext. That would be 1 and 17. I also know that if I take my key matrix and multiply by the next 2 characters of my plaintext, that would be 15 and 4, then I'll get the next 2 characters of ciphertext, which would be 13 and 1. So what this says, if you look at this first equation, this says that 7A plus 15B equals 17, and 7C plus 15D equals 17. In fact, the first equation is wrong. It should, instead of being 17, it should be a 1. Okay, and then over here, this next matrix equation says that 15A plus 4B equals 13. and 15C plus 4D equals 1. So now if we take those equations and we first just look at the equations involving A and B, what we wind up with is 7A plus 15B equals 1, and then 15A plus 4B equals 13. Okay, now we can also gather the C's and D's. So there we would have 7C plus 15D equals 17, and 15C plus 4D equals 1. Okay, now we can recast these two systems of equations involving A and B on the left and C and D on the right in terms of matrices. So, we can write this as, if we choose, we can write this as 7, 15, 15, 4 times vector AB equals 1 and 13. And this system of equations on the right can be recast as 7, 15, 15, 4 times CD equaling 17, 1. Okay, so notice in both of these equations that the square matrix on the left is the same. And if we can find the inverse of that square matrix over F29, then all we would have to do is take both of these equations and multiply on the left by the inverse of the matrix 7, 15, 15, 4, and that would tell us precisely what A and B are and what C and D are. Okay, so the next thing, so we're going to erase this stuff at this point, and we're going to focus on finding the inverse of the matrix 7, 15, 15, 4. Okay, since we're running out of room here, we're going to erase a lot of this work and focus on finding the inverse of the matrix that we had discussed a little bit earlier. Okay, so remember our goal is to find this key matrix, A, B, C, D, and we've done some calculations here that lead us to believe that there's this other matrix that if we can find its inverse, it will allow us to compute the key matrix. So the matrix in question that we want to invert, you might remember, is this one. It's 7, 15, 15, 4. And you might remember to find the inverse of a matrix, a 2 by 2 matrix, what you do is you swap the main diagonal elements, and then you change the sign on the off diagonal elements. And then you've got to take that whole thing and multiply that every element in that matrix by the multiplicative inverse of the determinant. Okay, so let's see what that would be over F29. So the 4 and the 7 stay put. Minus 15 in F29 is 14. That's because 14 and 15 add together to give 0. And the determinant of this matrix is 4 times 7 minus 14 squared. And if you compute that mod 29, you get 6. So you want the multiplicative inverse of 6. Now you might notice that if you take 6 times 5, you get 30, which is 1 more than 29. So that means that 6 times 5 is equal to 1 in F29. And that means that 6 inverse is equal to 5. So now what we're going to do is take every entry in this matrix, multiply it by 5, and then reduce mod 29. And when you do that, you wind up with this matrix. So it's going to be 20, 12, 12, and 6. Okay, so finally now we're ready to find these entries A, B, C, and D of our matrix K. So remember that if I want to get A times B, so this is from the previous slide that I had erased. If you want A times B, or excuse me, not A times B, but the vector AB, we're going to take this matrix, this inverse matrix that we just computed, which is going to be 20, 12, 12, 4, and we're going to multiply it by the vector we determined on the previous slide, which is 1, 13. And when you make that matrix product, what you're going to get is 2, 3. Remember, when you're doing these products, to make all of your calculations inside F29. Right? Likewise, CD is this same matrix that we determined, this 20, 12, 12, 4, multiplied this time by the vector 17, 1. And when you make this product, you get 4, 7. So that means that the key matrix for today is able to be determined by Eve, and it's this matrix. It's 2, 4, 3, and 7. Actually, no, this is wrong. Actually, the key matrix is this, right? So it's A and B are 2 and 3. So 2 goes here, 3 goes here. C and D are 4 and 7. So 4 goes here, 7 goes there. So that is the key matrix for today.